Okay, I'm going to begin right away so that I can try to give you as much time at the end of the period for some studying.
Thank you, Mr.
Okay? So let's jump right into, launch right into projectiles. Now all you should have come back. Why do I have extras here? One of each, you guys. Like, why would I have 3 of these? 4 of... Oh, what the heck? Okay, you should have 3 separate papers. Oh, you should have 3 separate papers. Okay? So the first one, Riley.
Yep.
Let's start off on the right foot here, this unit. The first one simply shows what you need to know for the test, which will be like in 2 weeks' time.
Wait, oh, you say 2 weeks?
Yeah, this one won't take long.
Oh my God.
This one, I promise, will not take long. Basically, here's how this one works. I'll do a day of intro. There's like 3 kind of like sample kind of days, types of problems, if you will, and then a couple of labs.
2 labs?
Yeah, a couple of labs. Basically, they are exercises, but real life. So you're going to be using the skills that you learn and applying it to real life, and we'll be seeing if we can predict where things are going to land. Sure.
This unit, is your part of minor diagram?
I am missing 2 classes.
No. Well, I don't know.
They're going teaching it.
I guess. I don't think it's any harder or easier, to be honest. So you will solve simple free-fall problems using the special equation for constant acceleration, which includes horizontal and vertical components of motion of the curved path of a projectile without air resistance. So we're going to be dealing with components. Draw free body diagrams for a projectile at various points along its path with and without air resistance. We will calculate the horizontal and vertical components with respect to velocity and position of projectile at various points along its path. And the big one, solve problems for projectiles launched horizontally and at various angles to the horizontal to calculate maximum height, range, and overall time of flight with the projectile. So mainly, there's not a ton of theory. In fact, there's very little at all. It's mostly problems. Basically, it's everything you've done up to now in motion, but now in 2 dimensions. Okay, and now that we've talked about components of vectors, it's easy to do. There are basically 7 types of problems, and I'm going to draw you a picture of what those 7 types are. They are on horizontal ground straight up. So, in other words, that kind of thing. Straight up, straight down. You did those in grade 11. Remember the rifle that was fired straight up, or?
Yeah.
It was probably gravitational fields. But now we're going to talk about gravitational motion and gravitational fields, but in 2 dimensions. Okay? Horizontal ground at an angle. So like this. Sort of like Evel Knievel jumping the fountains at Caesar's Palace.
Yeah.
Right? Off a cliff drop. So, sorry, did that one go away? Off a cliff drop. So in other words, you just go to the edge of a cliff and you go, like Wile E. Coyote, falling off the edge. Okay?
Like how long do you stay?
Good representation.
Yeah. Off a cliff drop. Off a cliff thrown. So in other words, you've been accelerated down. Okay? Those would also be considered to be grade 11 kind of questions, because it's only 1 dimension. Oh, we're going to get to that. Okay, so number 5, I think, is off a cliff, thrown up, then down.
Off the cliff stuff.
So you throw it up, and then it comes down.
Why is there so many off the cliff stuff?
Really, if you stop and think about it, really, 3, 4, and 5 are all the exact same. The only thing that's different is the initial velocity is either 0 or down or up. So they're the same if you want. Off a cliff projected horizontally. So now we're talking about what Ty's talking about, standing there at the edge and firing it like so, horizontally. And then the last one, the big daddy of them all, at an edge of a cliff, like that.
Like throwing frisbee.
Now, I will say now, that's the hardest one there is. There will be one on the test, there will be one on the exam. Guaranteed. Guaranteed.
You're on.
Okay? I'll also say if you have any Hot Wheels track or cars at home, I'll gladly take it off your hands. Because we could use a few bit more track on some cars.
What?
Hot Wheels cars.
And talk to Luke.
Yeah?
Wait, why? Why
Luke
do
who?
you need those?
Luke LaBelle.
Oh, yeah.
Oh, but you just asked me, like, besides the fact, I need Hot Wheels.
No, because we're going to do a lab with it. Yeah, I like to play with it. You got a problem with that?
Yes,
Okay.
because they're mine, and I
Oh.
want to get them.
Because it's right there.
I know. Oh, it's like a cult that I did, trying to convince kids. The 958-914 club. Mervin's part of the club.
What's it called?
Josh is part of the club.
What club? It's Greek.
Dawson was part of the club at one. Jared's part of the club.
It's computer science.
Oh yeah, and Hannah's part of the club.
They call it a club, but it's
Don't-
really
Can't say it's a
just-
secret
really,
club.
It's really just pretty.
We have
big.
secret handshakes.
Oh yeah? We do a handshake with Mervin. We do a handshake with Mervin.
Okay, so after this, today for sure, you're going to be able to draw the horizontal and vertical velocity vectors for a projectile at various points on its path and calculate horizontal and vertical components. So follow along with me, grab a highlight or a pencil or something. I'm on that third handout now. Yep, this one here. On the third handout here, this one here. Okay? So it says, earlier we discussed the vector quantities, velocity, and acceleration. Since only horizontal and vertical motion was considered, we did not need to know about vector addition or the techniques of vector resolution or vector addition. But for objects projected at angles other than straight up and straight down, we do. So a projectile is any object that is projected by some means and continues in motion by its own inertia. Then yeah, save it. A cannonball shot from a cannon, a stone thrown into the air, a ball that rolls off the edge of the table are all projectiles. These projectiles follow curved paths that at first thought seem rather complicated. However, these paths are surprisingly simple when we look at the horizontal and vertical components of motion separately. So we're going to separate X and Y components. Where have we done that before? Oh my goodness. What do you know? Coming back to the same things over and over and over again. The horizontal component of motion for a projectile is no more complex than the horizontal motion of a bowling ball rolling freely along a level bowling alley. If the retarding effect of friction can be ignored, the bowling ball moves at a constant velocity. It covers equal distances in equal units of time. See this? If I draw a line, a vertical line like so, it is pretty straight. And like every one of those is exactly the same. Where have we done this before?
Racing cars.
No, we did this a few minutes ago when you took the piece of paper and you did this, and someone said it feels like they're all kind of the same distance. That's because they are. They're supposed to be. Okay? Interestingly enough, the horizontal component of motion for a projectile is completely independent of the vertical component of motion. That is a key concept. In fact, if there's one thing that you need to know, it's that. That one statement tells you everything about this unit.
It's always going to be the same speed.
The horizontal motion of a component of motion projectile is completely independent of the vertical, okay? How fast it's going sideways has no relationship to how fast it's going up or down. If the up or down changes, does the left right change?
No.
Nope. Each acts independently of the other. Their combined effects produce the variety of curved paths that projectiles follow. So like when I toss the ball to tide, right, it has a horizontal, oh, that's a little lower than I expected, sorry. It's a good thing it's a full ball. It has a horizontal, well that's a higher angle. Higher, it has a horizontal velocity and it has a vertical. Now the horizontal the whole way stays, I'm not a very good thrower. The horizontal stays the
Same.
but the vertical does what?
Goes down.
It goes up. It goes back. It goes to zero, and then it speeds up coming down, right? Okay. And those act independent of each other. The multiple flash exposure of figure 2 shows equally timed successive positions for a ball rolled off a horizontal table. Investigate the photo carefully. Now, you guys have a copied version. Mine's a nice little color one. There's a lot of good physics there. The curved path of the ball is best analyzed by considering the horizontal and vertical components of motion separately. There are two important things to notice. The first is the ball's horizontal component of motion doesn't change as the falling ball moves sideways. The ball travels the same horizontal distance in equal times between each flash. Okay, so again, if I draw that line, let me make it in a different color. What should I pick?
Yellow, purple, pink,
I think I can do this. Pink?
Lime green.
How's that? Okay. So there is the edge of that first ball. Is that distance to there the same as to there? It's the same as to there? It's the same as to there? Sure is. Right? Which means this ball is traveling sideways at a
Constant velocity.
constant velocity. Well done, Riley. Constant velocity. Okay. The ball travels the same horizontal distance in equal times between each flash. That's because there's no component of gravity acting horizontally. Gravity acts only downward. Well, of course.
Really?
So the only acceleration of the ball is downward. So what is the acceleration horizontally? Big fat zero. The second thing to note from the photo is that the vertical positions become farther apart with time. Now that you'll notice here that they've got these lines here to sort of help us, but here's what I mean. I'm going to take this line and I'm going to flip it so that it's sideways. And now you can see the distance between there and there and there. And as I go down, they get, well, but the distances that I'm traveling, like look at how far, that's almost a whole grid, right? Here I've got like 1, 2, 3 in one grid. Here I've got just 2. What's the same though, Ty? I heard you say it. Yeah, did you notice that? That the red ball, that's because gravity's the same. Gravity doesn't know the difference between you just free falling, Tom Petty like, or being projected sideways.
That was a good joke, nobody got it.
Yeah, I know.
I did.
Did you?
That song's overplayed now.
Yeah.
I got it. Now the song's stuck in my head.
Sorry.
No,
Sorry.
don't worry about it.
Too soon? I think Tom would be happy that I'm using his song in my physics class. Not that I know him personally, but or knew him.
A few weeks ago.
The path traced by a projectile that accelerates only in the vertical direction while moving at a constant horizontal velocity is called a parabola. Where have you heard that before? Math class. Hooray for quadratic equations.
We can't bring back last year's stuff.
It's all the same stuff, you guys. It really is. Cosines in math is the same as cosines here. The only place cosines are different are in like, essentials math where they're talking about like, your mortgage, that kind of cosine. When air resistance can be neglected, usually for slow-moving projectiles, the curved paths are parabolic. Okay, now, hey, I've got,
Clickers.
not only have I got clickers for you guys, I've got brand new clickers. The first question is, at the instant a horizontally held rifle is fired over a level range, a bullet held at the side of the rifle is released and drops to the ground. So you fire your rifle, you drop a bullet at exactly the same time, right? One goes like this. Which bullet? The one fired downrange, the one that's fired horizontally, or the one dropped from rest just strikes the ground first? A, B, C, or D? Okay, let's go back to the theory here. We're not getting very. I gotta keep going. Okay, so upwardly moving projectiles. Consider a cannonball shot at an upward angle. Pretend for a moment that there is no gravity. Then, according to the law of inertia, the cannonball will follow the straight line path shown by the dashed line in Figure 3. So if you fired it and no gravity, it would just continue at a straight line. But there is gravity, so this doesn't happen. What really happens is that the cannonball continually falls beneath this imaginary line until it finally strikes the ground. Get this, the vertical distance it falls beneath any point on the dashed line is the same vertical distance it would fall if it were dropped from rest and had been falling for the same amount of time. This distance given by d equals 1/2 gt squared, or d equals vit plus 1/2 at squared, where t is the elapsed time. So in other words,
Another formula.
no, not really. In other words, after 3 seconds, the ball is there, which is the same position it would be if you were to drop it from there.
Whoa.
I'll say that again. After 3 seconds, if there was no gravity, it would be there after 3 seconds, right? Because of gravity, it's there after 3 seconds. This distance, this 45 meters, is the same distance that you would fall in 3 seconds. That's what this is all about here.
That's cool.
Okay? Note another thing from figure 3. The cannonball moves equal horizontal distances in equal time intervals. These distances here are the same. No acceleration takes place horizontally. Only acceleration is vertical in the direction of Earth's gravity. The vertical distance it falls beneath the imaginary straight line path during equal time intervals continually increases with time. Figure 4 shows vectors representing both horizontal and vertical components of velocity for projectile following a parabolic path. So here we have, at this point right here, that's the instantaneous velocity. This right here is the VV, vertical component of the velocity. Here in red, this would be the
Oh.
VH, right? Notice that the VH
Is just.
is
The same.
always the same. The VH is always the same. Why? Because there's no horizontal acceleration.
VH is horizontal.
What if there's
Yep.
wind resistance?
So why don't we use
There is a little bit of wind resistance.
Why don't we use X?
You can use X and Y if you want. Oh yeah. Do you want to call it X and Y?
Yeah, can we?
Sorry, yes. Yes. Okay. X and Y. Those are equivalent to each other.
Yeah, wrong way.
Those are wrong way.
You're right. I was just testing you. Just testing you. Yeah, I got 0. What about VV? Does VV change? Well, VY change?
Of course.
Well, of course it does, right? In fact, it goes from like the biggest value to the smallest. Okay. Where is this thing moving the slowest overall speed?
In the middle.
Right here?
Yeah.
Why do you say that?
Because it reaches 0. Or
The VY equals 0, but the VX stays the same, right? So here, like, let's say the VX is like,
Or no.
I don't know, 5, and the VY would be 10. Well, the total would be like 13 or so, right?
Yeah.
What's it going to be? What's the total going to be here?
5.
Just 5. So it has to be going, its overall speed is going to be the lowest at the peak, right? Okay. What if you're at a steeper angle?
Same thing.
Notice that the initial velocity vector has a greater vertical component than when the projection angle is less. This greater component results in a higher path. The horizontal component is less, so the range is less. Now this is the first time we've used the word range. This distance here is called the range. You know, it's where the deer and the antelopes play.
Ha!
Why doesn't it go so far? Because the horizontal speed is just little teeny tiny. Right? How can I get it to go farther?
If you had shot it,
Bring the angle down, or what if I were to fire at the same angle but faster? Would it not go farther?
yes.
It goes farther because it's actually in the air longer, right? Okay,
But if you shot it
we're
at the same
winding
time.
down here. Figure 6 shows the paths of several projectiles all having the same initial speed, but different projection angles. The figure reflects the effects of air resistance, so the paths are all neglects air resistance, so the paths are all parabolas. Now, if you're a golfer, you know that when you hit a shot, it tends to not follow that path, it goes up in the air and then it eventually drops like that, right? There's another name for that path.
Close your face.
I always forget what it is. It's like, oh, I don't remember what it is. I don't know.
Exactly like this.
It's like hitting a sand iron. It goes up and then it comes straight down, right? That's what you want. Notice that these have different horizontal ranges. Now, is there anything that you might notice about this picture? What's one thing that you might notice? Oh, I heard Christine say it. 75 and 15 land in the same place. And those add up to
90.
60, 30.
Well, what's with 45?
As long as
45 and 45. And it also tells you that the greatest range is at 45 degrees. And that makes sense, right? Are the components equal to each other at 45 degrees? Like, is the x and the y the same? Yes, you do know that. Okay, that's what this paragraph says. Here it talks about maximum range is attained when the ball is batted at an angle of nearly 45 degrees. In cases where the weight of the projectile is comparable to the applied force, it's like when a heavy javelin is thrown. Actually, the applied force does not produce the same speed for different projection angles. So heavy things, you actually want less than 45.
Yeah.
Yeah, okay? This is actually, with resistance, this is the golf thing, right? It tends to follow that path. Now, what we're going to do is this. We're going to get out Hot Wheels track. We're going to build ramps.
I have so many Hot Wheels.
Please bring it in. We're going to slide the Hot Wheels car down. It's going to jump into the air. And we're going to have to predict where it's going. We're going to calculate where it's... Ready? I have yellow.
I have black. Oh, I when I was a kid.
Bring it in,
My
John.
mom bought me this thing. It's like you put that on a wheel track, and it's like a board that slides it towards two tires and spins in it.
Oh, yeah? Cool. Oh, I remember that, yeah.
Yeah.
Okay, so here's kind of the check your thinking questions here. How much do you guys have these questions in front of you? Okay, so there's 2, 3, 4, there's just a few. Oh yeah, we got, oh. Okay, we gotta hurry so I can show you the videos at the end. A projectile is shot at an angle into the air. If air resistance is negligible, what is its downward acceleration? You need a number.
It's 9.8. It's 9.9.
A projectile is shot at an angle into the air, like this. If air resistance is negligible, what is the downward acceleration?
The same as when you shot it up.
I need a number.
9.8, isn't it better?
I don't know.
I need a number. Yes, you do know. You just don't realize it. Stop worrying about being wrong. Go with your gut. Oh. Oh, Dave, she must really be mad. What is the downward acceleration? Oh. Okay, hurry, so I can show you the videos. Because don't you want to see if Mythbusters can actually do the big slide jump? So hurry.
How do I cancel?
Can't.
The answer is minus 9.8.
Okay, now it's 42.
What is the horizontal acceleration? What is...
Why is it negative?
It's down. But I said downward. Remember, the negative just indicates direction. Dawson, Riley, and Veronica.
Oh.
Horizontal acceleration. Use those new good clickers.
Wait, what?
Horizontal acceleration.
Hey.
Go down.
Come on, it's not rocket science. Oh, I guess it is.
Oh my gosh.
Oh, never mind.
Every semester I use it.
Honest.
I got it.
0, yes.
Who got it wrong? Who got it wrong?
That wasn't me.
I've already answered this question. At what part of its path does the projectile have minimum speed? The smallest speed. At what part does it have the smallest speed?
Stop.
I don't mean after it lands. I mean at landing time that it lands. By the way, Brett, your bridge didn't quite... You've got a couple things out of place here.
Stomp on it.
Come on, Jackson. I told you this, you guys. The minimum speed is at the peak. Why?
Hey, what's my green?
Because you've only got the X component. Remember when I did this? Didn't I do it right here?
Yeah.
Okay, blah, 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 blah. Let's watch the videos.